The next technical committee presentation, that's TC 262 SCI, and that is considering the characteristics of the steel concrete interface and their effect on initiation of chloride-induced reinforcement corrosion. So the TC chair, Willy ANGST, will be presenting this overview, and it's a pre-recorded presentation, so I will launch it now.
Hello everybody, it is a pleasure to welcome you to the presentation of the Rilem Technical Committee 262 SCI, which is a committee on the characteristics of the steel-concrete interface and their effect on initiation of chloride-induced reinforcement corrosion in concrete. My name is Ueli Angst and I'm the chair of the TC, and I would like to present you the main outcome of this TC in the following presentation. First, I would like to start with a brief overview of the context, especially why we need to predict corrosion of steel in concrete. And I would also like to show you briefly what is the bottleneck in model developments. After that, I would like to show what are the contributions of our Rilem Technical Committee in addressing these challenges and in addressing to resolve the bottleneck for enhancing further model developments. We will do this by focusing on the following 2 points here. First of all, we looked at the characteristics of the steel-concrete interface in describing and characterizing them. And secondly, we looked at what are the influences of those characteristics on corrosion initiation in concrete. A very general introduction may be the following one. Why do we need to worry about steel corrosion in concrete at all? Some of you are for sure familiar with the study that was made in the US in the 1990s, which revealed that corrosion of highway bridges generates costs of around $8.3 billion each year, which at the time corresponded to approximately 0.1% of the gross domestic product. Just very recently, a study in Switzerland from 2019 revealed that corrosion of road bridges actually still has similar costs as in the 1990s in the US, namely around almost 0.1% of the gross domestic product of Switzerland. In Switzerland, this actually means that corrosion of road bridges generates direct costs of around 1,000 Swiss francs each minute. Therefore, it is important to study corrosion of steel in concrete. Another issue is that corrosion of steel in concrete is the most frequent cause for premature deterioration of concrete structures, as can be seen from this figure here that illustrates an evaluation of case studies from the UK, also from 1990s. Especially in the case of road bridges and in the case of marine structures, it is chlorides that are the main cause for corrosion of steel in concrete. Therefore, we need to be able to predict corrosion of steel in concrete in order to be sure that we can design durable structures and that we can predict when maintenance in existing structures would be timely. The established concept to predict chloride-induced corrosion in concrete is the following one. On the one hand, there is a chloride ingress model that permits to describe how chloride concentrations at the steel surface increase over time. So it is essentially a transport model to describe the chloride ingress into concrete. And then there is the option, of course, if we have data from a certain structure by drilling and testing on the structure, that we can validate or improve the chloride ingress model. But either way, at the end, we have to compare this to a threshold that is the limit state for the model. And this threshold is the chloride threshold value, which is abbreviated here as C-crit, sometimes also referred to as critical chloride content in concrete. And the concept is very simple. It means that once this threshold value is hit, corrosion will start, and therefore this point here defines the time of corrosion initiation. I would like to highlight that this is the only concept that exists and that all models are based on exactly this concept. However, if we take a closer look at the chloride threshold value here, which can be seen here from a literature review done a couple of years ago, you can see that this chloride threshold value scatters over a huge range of numbers. It starts at values that are virtually zero and goes up to values above 3% of chloride by 7th weight in the concrete. So of course, if this threshold value is uncertain or exhibits a high scatter in the literature, it questions the usefulness of such models to describe chloride-induced corrosion initiation. So this problem was sort of the starting point for our TC, because it was known already when we started in 2015 that other parameters, other than the chloride concentration, play a dominant role in corrosion initiation of steel in concrete. Parameters that were frequently mentioned in the literature at the time were pH of the concrete pore solution, steel potential, and the conditions at the steel-concrete interface. This third point here is relatively vague and may comprise a lot of different features, and that is exactly the point or the objective of our TC, to look into this in more detail. Our hypothesis when we started was that the local characteristics at the steel-concrete interface strongly affect the locally tolerable chloride content for corrosion initiation. And that was the hypothesis when we started, so it was the basis to look at the local characteristics that one can find at the steel-concrete interface. The aims of the TC were to first document the effect of different conditions at the interface on corrosion initiation, and also to identify areas of need for more research. We also wanted to summarize existing methods that are suitable to actually characterize, measure, quantify local characteristics of the steel-concrete interface, and finally, if possible, to prepare a recommendation concerning those methods. Before we look at the achievements of our TC, I would like to acknowledge the contributions of all our TC members. The TC had around 40 members that are all listed on this slide here. And beside myself, who acted as chair of this TC, Professor Mette Geiker was the deputy chair over the last 5 years. We had, after our first workshop in June 2015 in Oslo in Norway, we had 15 meetings in different places until today. So this means that we had on average 3 meetings per year. And it may also be worth mentioning that apart from the last meeting now in July 2020, all those meetings were held with physical places in different locations, both in Europe and in North America. The first milestone that we achieved was a paper published in Materials and Structures 2 years after the TC started. So in 2017, this paper was published, and the publication is entitled The Steel-Concrete Interface, which is a paper that describes the many different features that one can find at the steel-concrete interface. So we conceptually proposed this model where the steel-concrete interface can be understood as consisted of a part that is more related to the steel, so the steel part of the steel-concrete interface here on the left, and the concrete part of the steel-concrete interface. We are fully aware that one cannot separate things here very clearly, and that some features are intermixed at the steel-concrete interface, but to categorize the different features more easily, we suggested to divide it as follows. So on the steel part of the SCI, we have, for instance, the steel metallurgy. Then there may be different scales, oxides, scales and layers on the metal surface, such as illustrated here in orange. And if we move gradually into the concrete, we may have, of course, features such as air voids at the interface, bleed water zones. I will show a couple of figures later on to illustrate these. We may have cracks that come from the cover, and we may have cracks that are along or mechanical damage along the steel surface, such as slip and separation. And all those voids, they are interesting because they may have different moisture conditions also, as schematically shown here. So this void here would be in this sketch here fully saturated with water, while this air void here may be only partially saturated and may have adsorbed water on its surface, but otherwise it would be gas filled. So the moisture state of those different voids that one can expect at the steel concrete interface was something that we discovered has a pronounced influence on the corrosion behavior, and I will get back to this later on in the presentation here. So we came up with an extensive, rather extensive list of characteristics of the steel concrete interface, and I'm of course not going into details here today, but what you can see here is that alone at the steel in the steel chapter here, that is the first part, we have a lot of different features. Then we have some different features that are related to the steel surface, then to the concrete microstructure, and we have different macroscopic voids, such as entrapped or entrained air voids, bleed water zones, cracks, honeycombs, and so on. And then we have a lot of different miscellaneous possible local characteristics, such as tie wires, spacers, ducts, and so on. I will show a couple of examples there. In this table, we also looked at where those features are, if they are along the steel surface and on what scale. So some of those features are on the nanometer scale, for instance, the passive layer on the steel surface, oxide layer, but others may be up to the millimeter or even larger scales, such as, for instance, honeycombs or air voids. We also looked at the occurrence of those features, because some of them may only occur in on-site conditions in structures, while other features are more dominant in laboratory-made specimens. And this is an important point, which I also will mention later on. So just to give a couple of examples, on the steel side, the metallurgy and the steel surface can be different in different structures, in different laboratory samples, because reinforcing steel can have a different metallurgy or metal microstructure. Traditionally, many steels are of a ferritic structure, but then later on some steels were manufactured that have a ferritic pearlitic core, but then at the surface they are martensitic, tempered martensite surface layer. And of course, at the very surface, there may be mill scales or rust scales. Those mill scales, they can be cracked, so they have cracks and crevices typically, and these then are behaving as voids. Again, as I mentioned, that may have different moisture states depending on the exposure conditions. These voids may be water-filled or gas-filled. If we look a bit more to the concrete side of the interface, there may be those very famous entrapped and entrained air voids that you can see here. So this is a photograph where the rebar has been removed, and you can see in the imprint in the concrete, you can see macroscopic voids here present. Here in a section again, so we have some voids that just barely touch the steel, and in the figure on top you can see some voids that are really very at the interface and have a rather large overlap with the steel surface. Bleed water zones are also a well-known feature of the steel concrete interface. Here is a section that shows that at the upper side of the steel is the white part, there is a completely different microstructure than at the lower side, where we may have this macroscopic gap that is interspersed here with small aggregate sand and aggregate particles and some cementitious phases. And of course, the black part would be a void. So this bleed water zone is primarily a macroscopic void that again can have very different moisture states. Cracks are also well known. We may have cracks through the concrete cover, which is a very special feature because it not only changes the interface, but also the transport through the concrete cover. And then we may have local damage here, such as slip and separation and secondary cracks in the concrete. Some special features that have not received much attention were also covered in our review. So for instance here, if we have intersecting rebars, you can see a cross section here cut through two intersecting rebars. We can see the tie wires here, and we can see that if the rebars are close but don't touch them one another, there may be small voids formed in the interspace because, of course, it's more difficult to get the concrete properly compacted in those areas. So this is a feature that has not received much attention, but may play also an important role. And of course, spacers such as plastic spacers also dramatically change the condition at the steel, concrete, or steel spacer interface. The major conclusions of our first paper were the following. There is significant spatial heterogeneity along and around as well as perpendicular to the reinforcing steel bar in terms of both material composition and physical and chemical properties. The second conclusion was that the steel-concrete interface in laboratory-made specimens can often be very different compared to the conditions found in engineering structures. And this is very important because most studies on corrosion of steel in concrete in the literature were made on laboratory specimens rather than on structures. And if we now know that the steel-concrete interface can be very different there, of course, this questions the applicability of results found from laboratory studies to structural conditions. And finally, it was found that some of the steel-concrete interfacial characteristics are better documented in the literature than others. For instance, macroscopic voids, such as air voids and bleed water zones, are relatively well documented. Also, the concrete microstructure, rebar geometry and rebar microstructure are well documented. But on the other hand, there is a lack of documentation of the moisture conditions in those voids at the interface, steel surface conditions, and many other features such as rebar intersections, the influence of tie wires, welding points, contaminations, and so on. So we suggested that those features need to be documented better so that there is a need for more research and documentation for those features. The second milestone of our TC was another publication that was released 2 years after the first one in 2019. And so after the first one, we looked into the effect of the different steel-concrete interface characteristics on chloride-induced corrosion initiation in concrete. First, what we had to do is we had to develop a method to quantify the effect of different steel-concrete interfacial characteristics on corrosion initiation. And I'm not going into details here as it can be read up in the paper, but we came up with a mathematical formula that allowed to quantify and normalize the effect of different characteristics so that it allowed for comparison between those and that we could distinguish between a positive effect and a negative effect. So a positive effect would mean that a certain feature at the steel-concrete interface actually increases the resistance against corrosion, while a negative effect means that this feature makes it easier or more susceptible for corrosion to initiate. The big conclusion of this second paper, which covered a lot of literature studies that were all evaluated with the method that I briefly sketched on the previous slide, can be found on this slide here. So this is the summary of the different effects. Blue means positive effect on on this scale, logarithmic scale here, and yellow means negative effect. So for instance, steel surface polishing was found to have a dramatic positive effect. So if the steel surface is polished, we can make the system much more resistant against corrosion. But of course, this is something that is rarely done or never done in practice, but that can frequently be found in laboratory specimens. Also, the moisture content in the concrete was found to play a major role in terms of the higher the moisture content, the higher seems to be the chloride threshold value or the resistance against corrosion. Metallurgy of the steel also was identified as an important parameter, but there the literature was controversial. So there are studies that suggested that metallurgies deviating from the traditional ferrite phase have a positive effect, while other studies suggested that those metallurgies have a negative effect. The mill scale and rust layers are also a dominant feature, and there it was consistently indicated that they have mostly a negative effect. So if we have mill scale or rust layers on the steel, they would decrease the corrosion resistance. And then we had the interfacial voids. Again, this was controversial in the literature, but we believe that this can be explained by different moisture conditions in those different voids, depending on the exposure conditions. An important finding from our study was, however, that parameters such as cement type or water binder ratio have a comparatively moderate effect on chloride-induced corrosion initiation in concrete, at least from the perspective of the steel-concrete interface. And this has an important implication that I will get back to in a minute. Our results can also be plotted in a slightly different manner. So here we have the effect on the x-axis. So the features on the left have a moderate effect, and the features on the right here have a more pronounced effect. And on the y-axis, you can see the number of studies that we were able to collect. And there it is interesting basically to see that those features that have a small effect are the features that have received most attention in the literature, while those features that seem to have the largest effect are relatively rarely studied in the literature. So this means that features such as moisture content in the concrete and its influence on corrosion initiation, or steel-related parameters such as the metallurgy, seem to have a large effect, but they have rarely been, or they have only been studied to a very limited extent. On the other hand, there is no further need to look into the effect of water binder ratio or cement type on chloride-induced corrosion, unless the study, of course, is related to transport properties in the concrete cover. But if it concerns the steel-concrete interface, this has already been studied a lot, and at the same time it was found that it is not a very important parameter. So the major conclusions from this were the following. Traditional concrete technology parameters have a relatively small effect of corrosion initiation in concrete, but we don't want to say that they are not important at all. Of course, water binder ratios and cement types are still very important parameters for service life design and for ensuring the durability, because of course they play a role in the transport properties of the protective concrete cover. Based on our findings, we suggest that future scientific and engineering developments towards predicting corrosion initiation in concrete should not only look at transport modeling of chloride through the concrete cover, but should rather focus on the effect of steel properties, including metallurgy, mill scales, rust layers, and steel surface roughness, and also should consider the moisture at the interface, particularly in interfacial voids. It is interesting that corrosion in concrete has been looked at mostly from the perspective of concrete. So the steel properties have received relatively little attention in the literature, And we believe that this is an opportunity to be looked at in order to improve the way we can predict corrosion in concrete. And of course, the moisture is also a very important parameter that needs further study in this regard. A final comment, since it has been found that cement type and water binder ratio and other features related to concrete mix design have a relatively small effect on the chloride concentration that is needed to trigger corrosion. So therefore, we suggest that it doesn't make much sense to design test methods that are aimed to determine the chloride threshold value as a function, for instance, of cement type or water binder ratio. Such results from such tests will have very little relevance in assessing the durability because it is the steel properties, because it is the moisture concentration or the moisture content that seem to play a much more important role. What are the final steps of our TC? Well, our TC will be closed soon, but we still wanted to briefly also look at techniques that are available today for characterizing the steel concrete interface. There are a lot of different techniques that may be potentially used, but some of them are also limited because the steel concrete interface has properties that are difficult to measure. One example there would be the moisture in voids at the steel concrete interface, which is important, but at the same time is also very challenging in adequately quantifying. So we would like to evaluate and summarize what is the state of the art on this today and highlight what would be needed to improve in order to deliver the tools that are needed to better study corrosion initiation in concrete. In doing so, we will only focus on those interfacial characteristics that were found to be relevant for corrosion, such as, for instance, as I mentioned, the moisture content. And we hope, or we plan to have this completed in 2021. And I can also mention that the writing of this will be led by Dr. Hong Wong from Imperial College in UK. So thank you very much for your kind attention, and now I would be available for questions.
Yes, thank you very much for this nice overview of a very interesting study. Yes, indeed, we have maybe been focusing a lot on concrete and not on the steel part and its role in the corrosion initiation. Ueli, I hope that in the meantime, someone has been able to upgrade you to panelist. Yes, I can see so. So if you unmute your microphone, you can now also answer the questions, because I can see some questions in the question and answer section. There is a question actually quite interesting, especially for me, in relation to the TC on carbonation and its effects that I'm chairing. Did you consider the effect of carbonation on the layer concrete steel interface on initiation of corrosion in this TC?
Hello, can you hear me?
Yes, we do.
Yes, okay. So we did not explicitly look at carbonation. One thing that we looked at, however, was that on some construction sites, if typically there are different stages of constructing, and then it can happen that some concrete splatters are meeting some reinforcing steel that then is exposed to the atmosphere for some time until it is until the next batch of concrete is poured, and then so this steel may be covered partially already with, to some extent, pre-carbonated small areas of concrete, and then you would have an interfacial zone where carbonated concrete is already there from the beginning. But we did not find any literature study looking into this, so that was just listed as one thing that one should address in the future, perhaps.
Yeah, okay, thank you. I'm screening through the questions. Would the polishing not influence concrete reinforcement binding? So you saw it had a positive effect on corrosion performance, but maybe a negative effect on other properties.
You mean, well, polishing, the point why we listed polishing is because this is sometimes, or actually quite frequently it was used when preparing laboratory specimens, because people wanted to ensure that you have reproducible conditions. So to ensure that, the best way to do it is to polish the surface, because then you're sure what you have at the steel surface. But that is, of course, not very representative for practical conditions. And it has consistently been found that polishing the steel surface increases considerably the resistance against chloride-induced corrosion. So laboratory studies using that are for sure not applicable to practical conditions. But are you referring to, for instance, the bond behavior, or?
Yes, well, I
Yes.
think the question is that it had a very positive effect, you mentioned, but maybe there is also a negative effect regarding the bond. Yeah.
Yes, this may be, but the main point that we wanted to make is that polished steel samples are maybe nice from the reproducibility standpoint when doing laboratory studies, but it has nothing to do with the real conditions.
Mm-hmm. Yeah. Okay, there is also a question with regard to the chloride diffusion test anti-build 492. Is there a weakness of the standardized tests if you want to use this to study the behavior of the chloride ions, according to your opinion?
So this test primarily is a test to characterize the transport of chloride through the concrete. And transport of chlorides through the concrete can be tested with many different tests and can be modeled and so on, but we did not look at the transport. What we looked at is the chlorides, or the conditions that are actually needed to trigger corrosion. So the transport was not at all part in our TC work, and we completely excluded that.
Mm-hmm. Okay. Well, there is also a question when you say that the cement type has no effect, if the TC has addressed the effect of the soluble alkalis, since the pH is very relevant for the chloride threshold.
Yes, this is a very good point. Of course, if you do tests with a metal in a solution, the pH turns out to be one of the major influencing factors. But as soon as the steel is embedded in concrete, which is very different from a solution, because we have solid phases present, we have voids present. The voids may be water filled, they may be gas filled, and so on. So it's a completely different situation. And in that condition, there may be an overall effect of pH, but there is no literature or very limited literature data looking at the pH in a steel concrete interface system rather than a steel solution system. And of course, different cements may lead to different pHs, but there are other influencing factors coming from the cement. For instance, they may lead to different microstructure, pore structure at the steel concrete interface. They may have different chloride binding behavior. They may have different sorption, moisture sorption behavior, and so on. So it's impossible to simplify the cement just down to a matter of pH. And all the other effects that are related to the cement play complex roles, so that it is not possible to just say a pH that has more alkalis also increases the resistance against corrosion.
Mm-hmm. Okay, thank you for the complete answer. I see actually quite some other questions in the question and answer session, but we are now running already 8 minutes into the break. And although this is an online conference, I still think we have to respect a little bit the time schedule. But Ueli, would you be willing to type some answers, some short answers to those people? That would be very nice.
Yes, sure. I
Then,
can see the
yeah.
questions here, and I can type some answers there.
Okay, so everyone who still has a question asked, Ueli will do his best to give you a short answer. And we will now go for a